you. Happy to be here. So you'll notice that the title of this tutorial is a little bit truncated compared with the title that's in the program. And I think this is representative of the stage of the tutorial itself. So a few months ago, when I wrote the abstract, I was very ambitious, but my reach exceeded my grasp a little bit. And so we'll be reducing a little the amount of material covered compared with that very ambitious abstract, but I think we still have a lot of topics. So I will begin by giving a couple of examples of the kinds of settings that we'll be looking at, and then I will go on to address them in detail. So the simplest setting that I'll look at is that I have two distributions, P and Q, and I have samples from each. So I have, in this case, a sample of dogs from P and a sample of fish from Q. And on the strength of these samples, my goal is to decide whether the underlying distributions P and Q are the same or not. Right? So here I've shown this as a cartoon, but this is something that arises particularly recently when you have very sophisticated models, generative models of data. Sorry. I hope that if people cannot hear me clearly itself, so I will adjust it. So yeah, so basically as you're facing the board, on the left you see examples of handwritten digits. On the right you see samples from a sophisticated generative model by Battlements et al. And in their paper, they sort of gave this grid of samples on the left and on the right to Amazon Mechanical Turkers and asked them, like, can you tell which of these was generated by a computer versus human? And the humans were performing at chance level. But this is not to say that the distribution of the digits generated by the computer is correct with respect to MNIST, which it was trained on. So for example, one of the big issues with GAN training is mode collapse, so you're basically like under-dispersed. So the digits that you're creating are plausible, but you might be creating a smaller variety of digits than is represented in human writing. And if you just give these two grids to humans and ask them to tell them apart, then they might not be able to do that. But yet you've made a mistake in your learning of these distributions. So this is one setting. Second setting that we'll be looking at is goodness of fit. So in this case, I have these red points that you see on the slides are crimes committed in Chicago. So I'm sorry to have distorted Chicago's map here, but that makes it fit better on the slide. And I've modeled these with a very poor model, which is a mixture of two Gaussians. And generally speaking, we have our data, we have our model, we want to know how well the model fits the data, and we want to know where it is that we're making mistakes. So in this case, how can we indicate where our model has gone wrong and give ourselves a clue as to how we might improve it? So that's the second setting I'll talk about. Here's a third setting. So in this setting, I have a distribution over two variables, x and y, and I want to determine whether x and y are dependent or independent. So this is a nice example where I've got images and captions. So x is my picture, y is my caption. And so on the top we have a hound dog, and then the caption is an animal saying slobber and exudes a distinctive houndy odor. So the issue with this is that the caption doesn't say this is a brown animal with 4 legs and a nose and a tail. It's something that's a sort of complementary view of the object rather than being something that's easy to map one to the other. So for many of these cases, it might be very difficult to find the mapping from image to caption, and it might indeed require some expert knowledge about a dog to know which caption corresponds to what image. So in spite of this difficulty, it might be interesting to test whether these two are dependent without trying to figure out the mapping between the two. And that's going to be the third thing that I'll speak about. All right. So this is, I think, the overview. So the first part of the talk, I'm going to just address exclusively the problem of looking at differences in distribution. So I've got my P and my Q. I want some measure of distance between them. The simplest way to think about this measure is as a difference in means of features of the distribution. So this is a very simple and intuitive way. The second way that I'll talk about is I'm going to show that the distance, the maximum mean discrepancy that I'll introduce is an integral probability metric. So that falls within a class, a larger class of statistical measures, which include, for instance, the Earth mover's distance or the distance you're going to use in the Kolmogorov-Smirnov test. And this might just seem like a technicality that only handful of statisticians might care about, but this insight actually gives us a lot of useful information. For example, if we're using the LMD as a critic in adversarial networks, so I'll briefly touch on that. And then I'll go back to that example of troubleshooting gaps. Then the second part, I'll talk about goodness of fit. Just to give a little preview of what I'll use, I'm going to use a Stein trick to make this work. Then I'll talk about dependence testing. First of all, using maximum mean discrepancy, which I will introduce. But this isn't terribly informative or interpretable, so then I'll talk about a covariance-based way to measure dependence, which I think is a lot more useful if you're actually trying to get something you can understand. And then I'll talk about how to make a test out of that. And then, time permitting, I'll cover a little bit about additional topics, but that will sort of depend on, my time so far. All right, so first of all, maximum mean discrepancy. So let's start with this notion of a difference in expected features as a way to tell distributions apart. So here is our sort of statistics 101 example. I've got two Gaussians, they've got the same variance, they've got different means. How do I tell them apart? If I've got samples from each, well, I would say are my empirical means sort of far enough apart that it's unlikely to be due to chance. So the feature that I care about is just the expectation of the variable itself. But now let's say I've got two Gaussians which have the same mean but a different variance, right? So in this case, the expected feature that I might care about is the expectation of x squared. All right? So if I look at the distribution of x squared, it's chi-squared distributed, and indeed the means of these features are different for these two distributions. So if I computed them on the basis of samples, and I tested whether these expected means were far enough apart that it's unlikely to be a chance, then I would conclude that these distributions are different. All right, so next example, so now my means are the same, my variances are the same, and I might say, well, okay, I'll use the kurtosis. And then someone will give me two distributions which match in kurtosis, but they're different in other respects. So the challenge here is that for any single feature that I might choose, someone will always be able to give me two distributions that differ in other respects, but which match in that feature. So then you might think, well, what if I use infinitely many features and I can never be tricked, right? So the moment that you hear infinitely many features, a tool that should come to mind is to use kernel methods, because these are a nice mechanism for dealing with infinitely many features. So here's a very compact introduction to the tools that we might use in kernel methods. So if we have an object x, I'm going to define a feature map, phi of x, which might be infinitely long. It has to be square summable, so the sum of the squares of the features should still be finite, so it should be finitely long, but it might have infinitely many entries. All right? And I'm going to define a kernel as being dot product of these features. So any positive definite function will have a set of features whose dot product is that function. And so this is very convenient, because if I have an algorithm that only uses dot products, so if I express my algorithm only in terms of dot products, then I can deal with infinitely many features without a problem. So just to give an example, here's the exponentiated quadratic kernel. So most algorithms that you might download that use kernel methods will have that as their default, for better or worse. And here I plotted from Carl Rasmussen and Williams one possible set of features whose dot product is that kernel. So there's two things that you should look at in these features. So first of all, as the index goes up, so as we go down this list of features, they become less and less smooth. But also their amplitude gets smaller and smaller. So you're sort of saying, I'm going to have a function which is going to have more sort of low frequencies in it if I'm using these features. All right. So this is my feature map for this exponentiated quadratic kernel. All right. So these being my features, I talked about expectations of features, right? Because my representation of my probability is going to be an expectation of this infinitely long vector of features. And so I'm going to call this the mean embedding. So the mean embedding is just the expectation of this infinitely long vector of features. And just as we did when we just had the dot product of individual features being given in closed form by a positive definite kernel, the dot product of these expected features can be given as the expectation of the kernel. So I've got here the expected features of P, dot product with the expected features of Q. This is just the expectation under P and Q of the kernel between X drawn from P and Y drawn from Q. Okay? So again, this is very convenient. As long as my algorithm only depends on dot products between expected features, I can compute the dot product of these features in closed form, and I can run my algorithm, even though I've got infinitely many features. There's a fine print here, so I'm going to have fine print repeatedly for people who are sort of statistically aware, and that's something that you need to check, I think, to make sure that you can exchange the order of expectations and dot products in infinite dimensions. But as long as your code is bounded, that's allowed. All right. So these are my dot product of distributions. So now I want an algorithm to compare expected distribution features that depends only on dot products. So here's a very simple one. It's just the squared distance between the expected features. All right? And if we take this squared distance and we expand it out as the dot product of the difference in expected features with itself and expand out all the terms, then we just get the dot product of the expected features of P with itself, dot product of the expected features of Q with itself, minus 2 times the dot product of the expected features of P and Q. Bearing in mind that the dot product of expected features is the expected kernel, we now have an expression here which we can compute, as long as we can compute these expectations. All right. Now, if you think of a kernel as being a measure of similarity, because the dot product of 2 vectors should be large when the vectors are well aligned, assuming, of course, they have roughly the same length, then you can think of this as a sort of average similarity of a pair of points drawn from P. This is an average similarity as a pair of points drawn from Q, and this is the average similarity of P to Q. All right. So let's see what this looks like. So we'll go back to our fish and dogs example. So I'm going to do this now empirically. So I've got my 3 dogs, I've got my 3 fish. This matrix here is the matrix of kernel values between each pair of objects, right? So this entry here is the similarity between this dog and this dog. They're pretty similar, so the similarity is high. But the similarity of this dog and this fish is low. So the dot product of these features is small. All right? And now, what's our maximum mean discrepancy? Well, it's the average of this block plus the average of this block. So the average dog-to-dog similarity plus average fish-to-fish similarity minus the average dog-to-fish similarity. All right? So obviously, dogs are more similar to dogs, and fish are more similar to fish than dogs are to fish. So this quantity here overall is going to be large. But you can imagine a case where if you had just dogs and dogs, then this average plus this average minus twice this average is going to be something small. So you can sort of get a nice intuition as to why it is that this is a good measure of how far apart these distributions are. All right. So this is the intuition that comes from looking at differences of expected features. But I said that I would show that the quantity that I've just defined is an integral probability metric. So I'm going to now sort of attack this problem of comparing distributions from that angle. So here's a very simple example. I've got a set of points going from P, a set of points going from Q, and visually, if somebody gave you these 2 sets of points and said, well, is it likely that the underlying distributions are different, then most, I think, civilians would say yes. Whereas if somebody gave me these 2 sets of points, I would say, on the strength of what you've shown me, I think it's less likely that these 2 sets of points are from different distributions. So how do I formalize this intuition? This is one way that I could do it. I could say, well, I want like a well-behaved function, like in this case a smooth function, which should pull apart these expectations as much as possible, right? So the expectation under P should be very positive, expectation under Q should be very negative. And if I take this difference over like the best smooth function that I can find, if this is large, this is a pretty good indication that P and Q are from different distributions. And the smoothness matters. So if I use this same class of function for my second example, I can see that I can't pull these expectations apart quite as far, right? Because smoothness means that I can't sort of push my function up really far on the blue and really far down on the red. All right. So what is my class of smooth functions? For the maximum mean discrepancy, it's going to be a unit ball in a reproducing kernel over space. So a unit ball in the space of functions defined by the features that I started the talk with. So this enforces smoothness, this unit mole constraint. If we go back to our Gauss versus Laplace example, we see that this idea works in this setting, okay? Because you've got this smooth function here, which does indeed have large amplitude, where the distributions have large differences in mass, okay? So this now, I think, is a nice way to understand why this is called the maximum mean discrepancy. I'm finding a function from some class of functions that pulls apart the expectations as far as possible, so it maximizes the discrepancy in the means. So these are two ways of arriving at a quantity, but the link between them, the link between the MMD as I've written it here and the MMD as I've defined it earlier, which is the difference in expected feature means, like that's still, I think, a little bit obscure. So let's see how we might link these two things together, right? First of all, I should say that the function here, like how is it defined in terms of the features, right? This function here that I'm using is a sum of these features that I defined earlier, okay? So basically, like I've got an infinitely long vector of coefficients which multiply each of these features here to give me my function. And I've said that I'm in the unit mole, which means that the sum of these squared f's has to be finite, all right? And has to be 1, in fact, or less than or equal to 1. So this sort of shows me why it is that I have a smooth function, right? These nonlinear features decrease in amplitude as my index goes up, and I know that the sum of the squared f's has to be less than or equal to 1. So I'm sure that I'm going to get a smooth function out of this, right? And in particular, if I take the expectation of this function, just as I did before, I can take the expectation in and out of the dot product, subject to the kernel being bounded, and I can say that the expectation of that function is the dot product of f and the vector of expected features. So the dot product of this vector of coefficients and this vector of expected features under P. Just as a quick aside, I've mentioned that this is an integral probability metric. There are many different classes of functions I could use besides the RKHS. So if you use functions about variation 1, you recover the Kolmogorov metric, which is the largest distance between cumulative distribution functions. If you use bounded Lipschitz functions, you get the Stein distances and so on. All right, so now we've defined our function, so let's link these two notions of distance together. All right, so we'll start with this integral probability metric formulation for the maximum mean discrepancy, which is this function in a unit mole that maximizes the difference in expectations under P and Q. Now we use the thing that we defined a couple of slides ago, which is that the expectation of f is the dot product of the coefficients defining f and the expected features. Okay? So we will replace these expectations by the dot product of these coefficients and the expected features. And we do that for P and for Q. So now we have this expression. So now what is the function in the unit mole that maximizes this dot product? Well, let's look at this graphically. We have mu p minus mu q, so this is some vector in some high-dimensional feature space. I have some f, and I want to maximize the dot product of this f and the unit mole with mu p minus mu q. So what is the vector that does that? Well, it's not this or this, right? It's the unit vector that aligns itself with this vector here. Okay? So the best f, the f that attains the supremum, is the vector itself, mu p minus mu q, divided by its norm. So if I take now the dot product of mu p minus mu q with the unit vector in that direction, what do I get? I just get the norm of the difference in the feature means. So now we link these two notions of dependence together. I've got this norm of the difference in the feature means, which I've shown as an integral probability metric. The function view and the feature view are equivalent. All right, so I've defined my witness function in terms of an infinitely long vector of coefficients dot producted with an infinitely long vector of features. And this is a nice mathematical construct, but it doesn't tell me how I might compute my witness function in practice. Like, let's say I've got samples from P and from Q, and somebody asks me, well, what's your witness function here? So I'm going to now show you how to construct that witness function, and then I'll prove to you why it is that my construction is correct. Okay? So here are my samples from P and from Q. I've got my chosen kernel, which is my dot product between my features. I just put these kernel bumps on all of the samples. So red bumps on the samples from Q, blue bumps on the samples from P. Here it's an exponentiated quadratic kernel, but I could use other kernels as well, like energy distance kernels or inverse multi-quadratic kernels and so on. I add the bumps together now. So I add all the blue bumps, I get this blue function. I add all the red bumps, I get the red function. I subtract the red from the blue, and that's my witness. So indeed, it has positive amplitude where there are more blue points, and it has negative amplitude where there are more red points. So I have just computed this function without ever having to deal with infinitely long vector features. How is it that I did that? Well, let's go back to my expression for my witness. So my witness is proportional to the difference in expected features under P and Q. Okay? My empirical vector of expected features is just the empirical mean of the features for each of my xi's. Okay? Now, my empirical witness is going to be the dot product between this. My empirical witness evaluated at point B, right, is the dot product of this f star and the features at B, because that's how I define my function. It's the sum of the features with these coefficients. So I'm going to replace my f star as proportional to the difference in the means. Of course, we want to normalize to make a unit length inner product with these features. And then this last line, you remember that the dot product of the feature of xi and the feature of b is just the kernel between xi and b. And so this is the expression that we had, which we just constructed on the last slides. So the strength of using the kernels is that we can compute this witness, again, without having to deal with these infinitely long vectors of features, because the witness is entirely expressed in terms of dot products. All right, so we've defined now our criterion. We've shown that it's an integral probability metric. Now we want to, now we want to use it in hypothesis testing. Okay, so if I have this statistic and I compute it on the basis of samples, how does this help me decide whether P and Q are from the same distribution or from different distributions? So, roughly speaking and intuitively speaking, I want to make a decision depending on how large this statistic is. So if the empirical statistic is in some sense close to zero, I would accept the hypothesis that P and Q are the same. I think it's likely that P and Q are the same. Whereas if my MMD is far from zero, then it's less plausible that P and Q are the same. So that's sort of an unlikely thing. So what I want is to define a threshold. Like at some point I want to make a cutoff and say, well, if my statistic exceeds the threshold, I think it's unlikely that P and Q are the same. So I reject the null, and if the statistic is small, like smaller than this threshold, I want to accept the null. So for this, I need to get a sense of how this statistic behaves when I compute it from samples. Like I know what it does in population. It's 0 when P and Q are the same. It's not 0 when P and Q are different. But I want to now understand what's going to happen when I compute this on the basis of samples, because it's not going to be exactly 0 or not 0. Right? So let's do an experiment. We're going to draw 200 samples for each of P and Q and compute the maximum mean discrepancy. So here I've got P and Q. They're clearly different here. Root n times the maximum mean discrepancy is 1.2. So the reason for root n is going to become apparent in a couple of slides. Just run with me here. So this maximum mean discrepancy is not 0, as one would expect, because P and Q are different. So in this case, I think Q is a Laplace distribution with a bigger variance in P. So let's put this on a plot. So on this axis, I'm going to put the values of my empirical MMD. And here I'm going to say, like, what's the probability of having seen that value? Since I've only seen one, because I've only done one experiment, I just get a spike here at 1.2. Let's do it again. So I'm generating now 2 new samples from P and Q. Here my MMD is 1.5. Okay? So it's again large, it's not the same. I put that on my plot. And let's now continue this experiment. So now let's do it 150 times, 300 times. The flight from Australia to London is very long, so 3,000 times. And you can see that this is looking a little bit like a Gaussian. Okay? And indeed that's the case. So basically, how does this MMD behave when P and Q are different? It behaves like a Gaussian. If I generate many MMDs, it's going to have a normal distribution. Okay? And this normal distribution is going to be centered on its mean, and the variance of this is going to drop as 1 on n. So it basically gets tighter and tighter as I see more and more samples. Okay, so that's how maximum mean discrepancy, the empirical maximum mean discrepancy, behaves in the case that P and Q are the same. All right. So now let's say that P and Q are different. Very important. Okay. So now let's make P and Q the same. So here P and Q are just standard normals, one-dimensional standard normals. Very, very simple, all right? I've generated 10 MMDs. What you'll notice here is that some of these are negative, which might initially surprise you, right? Because P and Q are the same. I'm computing an estimate of a square distance between P and Q. Why is that ever negative? The reason for this is that I'm computing an unbiased estimate of this square distance. Okay? Because it's unbiased, and because the mean is 0, I'm going to expect to see empirical values above and below 0. Because the average is going to be 0 in the infinite sample limit. So that's why I'm seeing like negative ones. Okay? So 10 MMDs, 20 MMDs, 50, 100, 1000. I'm adding more and more, but this is still not looking like a Gaussian. And indeed it isn't. So unfortunately, when P and Q are the same, the asymptotic behavior of the maximum mean discrepancy is quite tricky. So n times the empirical maximum mean discrepancy has a distribution which is an infinite weighted sum of chi-squareds, independent chi-squareds. And the coefficients of this infinite weighted sum are a little bit hard to learn because they're the eigenvalues of this eigenfunction equation, which is a function of the kernel, which we know, and also of the distribution P, which we don't. So these coefficients are, themselves tricky to get, and the distribution is a sum of weighted chi-squareds with these weights. So the asymptotic behavior of the MMD when P and Q are the same is, I think, very technical to figure out. Okay, so now let's summarize what we found. We've seen that here I've got on the x-axis n times the empirical MMD, because it's n times the MMD that has this distribution. That's got this infinite weighted sum of chi-squared distribution. And then if P and Q were different, I would have a normal distribution. And because I'm multiplying by n rather than root n, this mean is going to diverge. All right?
So these asymptotics don't depend on the kernel chosen?
Oh, they absolutely depend on the kernel. So remember that the infinite weighted sum of chi-squareds depends on the kernel here, right? Because the weights are the eigenvalues of this eigenfunction equation. And I didn't show it here, but the variance that I get in the Gaussian, this is also kernel dependent. So if I choose different kernels, I'm going to get different means, different variances. So these distributions absolutely depend on the kernel choice.
So, but for any kernel, the asymptotically the MMD metric is Gaussian.
So for any kernel, the asymptotic MMD when P and Q are different is normal.
Okay.
With this variance, it depends on the kernel choice. When P and Q are the same, the asymptotic distribution is this monstrous thing, where the coefficients also depend on your kernel and on your P.
I mean, at this point, I was curious whether, can't I just see whether it is looking like Gaussian or not? And if it's not Gaussian, then probably P is equal to P? Or is that a bad reasoning?
So to do that, you would have to basically have access to, say, 500 samples of your thing, right? Because, yeah. So if you did, then you could. But if you did, then you'd just put all your samples together and just run one test. Yeah. So here is our summary. And so what do we want to do with the tests? What we want to do is we want to find a threshold. So now I have actually a sensible definition for my threshold, which is some high quantile of my null distribution, right? So that if P and Q are the same, then with some low probability alpha, I will exceed that threshold. So that would be a sensible definition for a threshold for my test. And this false positive rate is something that I would define as a user. Now, here I have the false negative rate. So if P and Q were different, then with some hopefully low probability, I might still fall below this threshold. Though, fortunately, as I see more and more samples, this mean is going to drift off to the right, and the probability of this occurring is going to drop to 0. So that's nice. Yep?
As I'm looking at that red curve there, which is the infinite sum of chi-squares, it seems to look to me pretty close to a gamma. So is it possible that I could just take one or two sums of that and get a pretty good approximation?
So that's a very good point. Indeed, it looks quite close to a gamma, and a nice trick to do is to approximate it by a gamma. And then you get something that runs a lot faster than the method that I'm about to tell you. The issue with approximating it by a gamma is that I can create distributions that will make that approximation poor. And so you have to be a little bit careful when you do that. But as a first pass, like as a sort of data exploration strategy, it's not a bad strategy to use. But unfortunately, if you do that approximation, then your test is no longer consistent. But yeah, that's absolutely a good idea to do. Yeah. So gather approximation is one approach. But if we want to test that it's still consistent, we're going to have to pay a little bit more computational cost. Okay. And the approach that I'm going to propose to do this is going to be a permutation approach. So let's see what this looks like. Here's my sample from my dogs. Here's my sample from my fish. Here is my maximum mean discrepancy, which is the average of this plot, the top right, top left, plus the average of this plot, the bottom right, minus these averages here. Okay, the off-diagonal plots. So now I'm going to take all my dogs and my fish, I'm going to put them in a bag, I'm going to draw half of the contents of that bag and call it x tilde, and the other half I'm going to call y tilde. So now I've got x tilde and y tilde are sort of murdochs, they're sort of fish-dog hybrids. Okay. And now let's look at this, the ground matrix that we get here. So here is the matrix of kernel values between my x tilde, the scrambled fish and dogs, and my y tilde, the scrambled fish and dogs. And in this case, you can see that these blocks here are on average, roughly the same as these off-diagonal blocks. So this is good because we're able to sort of simulate, using this permutation, the case where P and Q have the same distribution. So P and Q here are equal mixtures of the samples from P and Q. So this is a nice graphical illustration. Does it work? Well, yes, it does actually. And you can show that it gives you a consistent estimate of the null distribution. So you can use this permutation approach to get estimates of these quantiles of your null, and then use those for the test. So, of course, this costs, it has some computational cost, but it's also a good default because you're going to pay some cost, but it's not going to go wrong. Whereas other approaches, you have to be a little careful. All right, so this is how we get our threshold. We use the 1 minus alpha quantile of this distribution that we get from permutation. All right, so this is now a test which has been defined in terms of a kernel. And a question that I often got when I gave talks about these tests was, how do you choose your best kernel? So that's, I think, a reasonable question, and I'm now going to give an answer to that. All right. So remember that we have test power, right? Test power is a probability of correctly saying that P and Q are different. So if P and Q really are different, we correctly make that judgment. So that means the probability under the alternative of our statistic exceeding this threshold that we've got. Yeah?
What's you haven't specified, I mean, the alternative here is a composite alternative, right? I mean, so what's the definition of the alternative?
So here, P and Q, like let's say we have two samples. The true P and Q are fixed, right? And so we've just got two samples, one from P and one from Q. So when you say it's a composite,
sorry, so the null is that, so you have two distributions, P and Q, and they're null T.
Well, by the sample
null is that you had P and P, and then the alternative is that you had P and Q.
So that's a good question. So the null here is a very interesting thing to define. So let's say we've got two samples, right? Now, in the case where the null is true, then there's no ambiguity, right? P and Q are the same.
Right.
Now, in the case where the null is false, then, as you say, it's kind of tricky to define what you mean by null. Does null mean that both of them are P? Does null mean that both of them are Q? Does null mean that it's an equal mixture of P and Q? All of these are like plausible and reasonable definitions of a null. In the end, it doesn't really matter which of these three you use, because all of the three of them are going to give you a threshold which is correct when P and Q are the same, and which is fixed when P and Q are different. So basically, as I see more samples, my test will be consistent, which is to say this error here is going to go down to 0, whether I define my null as P and P, Q and Q, or P plus Q on 2. Does that make sense?
Yeah.
So
yes, that makes sense. So I guess maybe my question is, P and Q are pre-specified. Is that?
Or we have just samples from them, but we don't know them, of course. We just know them via the samples.
I guess the point is, if P and Q are arbitrary, then I can make P arbitrarily close to Q.
Yep.
So I can always make your power 0.
That is correct. So let's say I have 20 samples, okay, and I have freedom to choose P. I could choose P to make this overlap huge. But as the number of samples goes to infinity, this error is going to go down to 0. So for a given number of samples, I can have an arbitrarily high rate of false negatives. But as the number of samples goes to infinity, that will drop to 0 at rate 1 over 10, as it turns out. So another way of saying this is like when I have a fixed number of samples, I never really know. Like this is why when we say we have a hypothesis test, we either accept or reject the null. The terminology is sort of there because you can never like accept the alternative. Because to make a concrete statement about the probability of the false negatives, you have to restrict your space of alternatives, and which you can do, but which we won't do here. Okay. So how do we choose the best kernel? So we've got this probability under the alternative of exceeding this threshold. So this is basically the probability of correctly rejecting the null. All right. And because we know that under the alternative, the distribution of our statistic is asymptotically normal, we know that this probability, when we have enough samples asymptotically, looks something like this, where this is the cumulative distribution function of a normal. We've got our, our population MMD divided by the variance for a sample size n minus this test threshold also divided by the variance. Okay. So a nice thing happens here, which is that we know that the variance drops as 1 on n. Okay, as we see more samples, we're more and more confident. So this quantity here drops as 1 on root n, and this quantity here drops as root n. So when we're trying to maximize our power, we might be worried that the kernel has some obscure effect on the C alpha. Okay, and it does. I mean, the test threshold is a quantile of a distribution that depends on the kernel. Absolutely, changing your kernel will affect the C alpha. But if we have enough samples, the main thing that will have an effect is to just maximize the MMD divided by the variance. I basically want to make my MMD as large as possible and its variance as small as possible. And that's going to be enough in this case. So for a large enough sample size, the effect of the kernel on the C alpha will be much smaller in its impact on the power than just by making the MMD large and its variance small. All right, so this is what we do. This was a paper that appeared in ICLR this year, and we have the code on GitHub, so you should play with it. But this is what we have done to choose the best kernel. One important thing to bear in mind, though, is that when you optimize, you need to optimize on a held-out set, not on the set that you're testing on. Because if you adjust the kernel on the same set that you're testing on, you will get way too many false positives. It won't work. Okay, so this is, I just wanted to put this figure up again to remind people what we're doing here. We're basically taking this blue curve, we're pushing it as far to the right as we can, and we're making the variance as narrow as we can. So that's what we're doing. All right, so now, yep.
How do you solve that optimization problem?
We solve it by naive methods. So you might have better methods to solve than we did. So we just initialize a bunch of places, gradient descent. Yeah.
Okay.
So
it's not like we get the right answer. It's like
So we don't do anything fancy. I mean, if our kernel family is a weighted sum of kernels, then you can make it into a QP and it's nice. If you're optimizing, say, bandwidth, then it's not nice. Yeah. So now let's look at this MNIST versus GAN example. So now I've got samples from MNIST, I've got samples from my generative model, and I want to determine how it is that these distributions differ. All right. So the kernel that we're going to use here is basically going to have a parameter for each of the pixels in these images, and this parameter is going to basically not be small, so it's going to be large for the pixels that matter. So think of like an exponentiated quadratic kernel, which is has a different length parameter for each of the dimensions, and I'm going to learn using my best kernel strategy those dimensions that matter, that are most relevant to telling these apart. So this is for those familiar with Gaussian processes, this automatic relevance determination kernel. The test power that we get using this kernel, using this learned kernel, is 1. So basically, like if you use this kernel and you optimize it, using this sort of power maximization strategy, you will always find correctly that the GAN samples are different from the MNIST samples. By contrast, if we just use a naive RBF kernel without learning the link scales using our test power maximization strategy, we're doing a lot worse. Okay, so our false negative rate is a lot higher. This map here shows the relevant pixels, and it's quite neat because you can see a sort of line down the middle and a ring around the outside. So these are the pixels which are the places at which the GAN gets it different to MNIST. Another way that we can look at the outcome of this experiment is by seeing where the digits fall in the witness function. So what we have here is, a histogram of the values of the witness function at all of the digits, like the GAN digits, the human digits. And the blues are sort of indicating where a human has made their digit, and the reds are indicating where our GAN has made its digits. So you can see that a human overrepresents vertical ones compared with what the GAN does. And that is consistent with this bar of pixels down the middle here. Okay? Whereas like the GAN has some occasional sort of quirky things like this sort of 8-3 hybrid or this 6-5 hybrid. So these are things that are more representative of a GAN and less representative of a human. So these are nice visualizations. So this is
just a quick question.
Yep.
So based on this analysis of how the GAN is performing, what would you do to correct this?
We might, for instance, use this to train the GAN. So that could be something that you could do. So in a sense, like the GAN that was trained here was using this Jensen-Shannon divergence, so it's a sort of different divergence measure. You might want to sort of incorporate some of the information here into the critic of the GAN, which would then push it towards making fewer of these errors. So that brings me to my next slide. Can you actually use the maximum mean discrepancy as a critic for the GAN? So basically, what is an adversarial network? You have a generator, it's generating samples. You have a critic which tries to compare those samples to the set of reference samples, like real samples. And it seems a very natural use for maximum mean discrepancy. And indeed, it's an idea that was proposed quite a while ago. So in ICML and in UAI, actually, there were 2 papers that appeared at the same time where the MMD was used as a GAN critic, as a way of training the GAN. And what's interesting, this paper here was focused actually mainly on handwritten digits. And the reason for this is that when you're using just vanilla MMD on image data, it's a little difficult to get it to work well. And so what you might actually want to do is not use just MMD on the image data, but MMD on convolutional features of the image data, because we know that convolutional features are the good thing to use if your goal is to compare or to make inferences on images. What Rich Semel's group did is actually to do that. So they used an autoencoder network to get features of the images, which meant that their method as a practical algorithm was actually much, much better. But of course, then that sort of pulls you a little bit away from the GAN idea because you've got a separate autoencoder which is learning these features, so it's a sort of hybrid model. And so this brings us to 2017, where a lot more progress was made. So recently, people have been using a different integral probability metric, which is a Wasserstein distance, to train adversarial networks, so that's a critic for the adversarial network. Or there's also this paper by Marco Culturi last NIPS, where he was training Boltzmann machine using Wasserstein. So it's an idea which had a couple of papers come out recently. And what's interesting is that because Wasserstein is an integral probability metric, the tricks that can be used in training Wasserstein GANs, we can apply also to training MMD GANs, because it's IPM, it has a witness function, all of the same tricks apply. And indeed, we've got the WMMDs here, which are methods that use the Wasserstein training tricks to train MMD GANs. So this first paper here from CMU used the original Wasserstein GAN weight clipping tricks to train their MMD GANs. The second paper here used this more sophisticated, improved Wasserstein training technique to train the GANs. So just to give you quickly an idea of what's going on, this paper here, what it did is it said, like, between the samples from P and Q, so somewhere in between these two sets of samples, I want my witness function to have a gradient that doesn't vanish. So they just said, like, let's make a penalty for making that gradient far from 1. Okay? Now they can do that because they've got a witness function. The Wasserstein distance is an IPM, it has a witness function. The MMD has a witness function, so you can do exactly the same trick, and indeed that makes it train a lot better. And that's what these guys do. But that's not the only way to make it work. So also this year, there's a set of papers coming out of IBM which incorporated variance in different ways to basically train MMD GANs. So this first one, which was actually just appearing a couple of days ago at ICMO, used both mean features and feature covariances as their sort of like feature representation. This new one, which I think is submitted to NIPS, was using a Fisher statistic. And if you think about test power, where you want to maximize the difference in means and minimize the variance, a Fisher statistic is a kind of simple way to think about that. So these papers are quite orthogonal to those, but yet they work well. Yeah?
So I'm not sure to follow the previous slide before you got to this one. So looking at the analysis, so these ones.
Or could you speak up a little? Sorry.
Yeah. So first of all, how do we tie the deep learning models properties to the feature representation? So one way to look at it is just look at the inner product of two neural network of one input, another input, inner product of features. You have find the features.
Yep.
So this is a very multi-dimensional features. It's just a function.
Okay, yeah, no, that's a good point. So let me just quickly answer that question. So the question, if I understood it correctly, was like, is it that you're just saying, for your critic, that your kernel is the dot product between convoluted features, or is it the case that your critic is defined in terms of features entering into then a kernel and computing the MMD on that? Is that your question?
That's one.
So I'll answer, I guess, that one then first. So basically, both approaches are possible. These approaches here are the second one. So you basically have your convoluted features, and then on top of this, you sit a kernel with an infinite feature space. And that works. In this case, you just use a linear kernel on explicitly defined features, and that also works.
Okay.
So, yeah, so all of the above.
So why do these work in practice, and why do they not work?
So these papers all came out recently. I'm very interested in that question. And I don't think that there is a firm conclusion yet, because these are two different things that both seem to be working and are doing very different stuff. I mean, I have this other one here, which is doing something else again, which I haven't yet quite figured out. So, but all of them seem to be working, and all of them seem to be ways in which we can get an MMD style distance as a critic for GANs. But we don't know yet, like, what is essential and what is sort of peripheral. Yeah.
One last question is about mode collapse in GANs.
Yep.
How does that relate to these?
So the good thing about using MMDs is that it's very nice at detecting mode collapse, right? Because if your modes collapse, right? If I wanted to go back to my graph matrix, right? So let's say that this was sort of like the same. Like let's say that okay, I'm in a GAN situation here. So the top are my real dogs. And let's say the bottom, which is my generator, let's say that that's this first dog repeated over and over and over and over, right? Then clearly, the MMD is going to be large, right? Because the average of this will be like the average inter-dog distance for real dogs. But then this thing here is just going to be the same value repeated over and over and over, right? And then these things here are going to be sort of, whatever the distance from that dog to all the other dogs are. So I'm going to catch that pretty fast. Sort of as an aside, that's a good reason why using a distance between samples is better than using a classifier if you're going to do a critic for GAN. Okay. So yeah, so basically, like, these methods work. An interesting thing also is that, like, there is an art to training GANs, and this art matters. So basically, Lydia Yu, who's one of my Jordan's PhDs, so she used the same kernel as this group used, which is the kernel based on the energy distance. in her master's thesis. And because she wasn't using, I think, the gradient penalty when she was training, like she had trouble making it work. So it's sort of like, what makes a GAN work is a combination of using the right kernel and using the right training strategy. And that combination, I think, is a sort of art form which is evolving, and we don't yet have a complete solution to that. All right, so that's my sort of GAN aside. All right, what I'm going to do now, actually, rather than talk about this, I'm going to switch to this guy. Yeah, I hope someone will tell me when I'm talking for too long and shut me up. But meanwhile, I'm going to talk next about testing against a probabilistic model. Okay, so this is what happens when you have like, I mean, this figure is our initial MMD figure, right? So let's say that, you know, here I've got an MMD between, in this case, a Gaussian between 0 and a Gaussian being far from 0. Okay, and then I've got my witness function, which is a smooth function which has large amplitude where the probability mass and P and Q are different. All right. Now, previously, when I computed the MMD and I computed the witness function, I had samples from P and samples from Q, and I showed you how to compute the witness function in this case. All right? But now it might be that rather than having a sample from P, I might have a model P. Okay? And I might want to compute the MMD between a sample and the model that I think should be a good fit for that sample. So this could be challenging, right? Because if your model is very complex, then computing the expectation of some function with this model might require me to do MCMC or something difficult. So, you know, if I know my model only up to normalization, I can't compute this expectation. Even if I could normalize it, it might still be challenging to compute this expectation. Okay? So what do I do in this circumstance? I want to get rid of this expectation here. And the way that I can do this is to use this trick that comes about through Stein's method. Okay? So what is the, if I have a function f, I have an operator that I can apply to this function that will make its expectation 0 under p. Okay? So what does this operator look like? It's just 1 on p times ddx of f times p. So this looks a little bit obscure right now, but it turns out that the expectation of tp under p is indeed 0. Okay? Let's see why this is. Expectation under p of tp, I'm going to expand that out. It's 1 on p dx times p. These cancel. I've just got this expression here, the integral of dx of this. As long as this product vanishes on the boundaries, then indeed that's 0. So that's pretty quick. Okay? So this is my Stein operator. So now I could replace my maximum discrepancy with something I'm going to call the kernel Stein discrepancy, where rather than using f here on its own, I use f which I've passed through this TP operator. So if I pass f through the TP operator, then this term vanishes, and I'm just left with this thing here. So what does my witness function look like once I put it through this Stein thing? What it's going to do, like, remember that p is my model distribution. I made the expectation that the p vanish. My witness function just has now large amplitude, where q has a lot of mass and p doesn't. But it doesn't have it doesn't have the sort of corresponding positive bump where p has much more mass than q. So it's sort of telling me where it is that q has a lot of stuff that p doesn't. And as p and q, as these means approach each other, this function is getting fatter and fatter. And indeed it will be 0 when the distribution is coded Stein. All right, so, you know, I've defined this statistic. Just like the MMD, I can compute the kernel Stein discrepancy in closed form. This is what it looks like. It's the expectation under my sample of this hp quantity. Now, this quantity is a function of the derivatives of the logarithm of p and the derivatives of my kernel. The advantage of having a derivative with respect to x above px is that the log partition function goes away. So even if I can't normalize my p, if I only know p out to some constant, I can still compute this quantity, and I can still test whether my model is a good fit to my data. So I don't need to normalize p, I don't need to sample from p, I can just write this thing down. So now let's go back to my Chicago prime data. So here is the data. So, I think it's a nice saying well known to UAI attendees. It's like, no model is good, but some models are better than others. So here is a Tor model, which is a mixture of two Gaussians. And on this model, I want to figure out, like, where has my model gone wrong? And I can compute my witness function for that model. And you can see that it has large amplitude here and here. So what we'll notice is there's a sort of sharp threshold here where the crimes sort of stop. Okay, that's because that's where Lake Chicago starts. And so people commit their crimes up to the edge of the lake, but not in it. And that's what we're seeing here. If I use now a mixture of, say, 10 Gaussians, I'm now able to see sort of where that mixture is going wrong. So generally speaking, mixtures of Gaussians are not going to give me sharp edges, so they're going to have difficulties in these places here. But this witness function is going to tell me where my model is wrong. So this is a simple illustration. Again, I've got code for this online, so you can use it. Other settings in which these have been used. So one very nice topic recently is approximate MCMC methods. So if you're doing metropolis hasting, say, and you're computing your likelihood, that's going to require you to pass through all your samples. So you might try and approximate metropolis hastings in a way that will cause you some error, obviously, in your estimate of the posterior, but which might be a lot faster to compute. And so, this is something you might want to test. So you might want to say, like, if I'm drawing, 100 samples, is my estimate of my posterior sort of good enough that I would, if I did a test, I would accept the null for 100 samples. Obviously, if I do 1,000 samples, I need to make my NH a little bit better because I'm looking at more samples, so my closest to the model is being evaluated more rigorously. And this is something we can do. We can make a statistical test using this statistic to evaluate the quality of our approximate metropolis hastings methods. Next question might be which kernel to use. And it turns out if you're using these Stein tricks that the exponentiated quadratic kernel is not too good. It's still consistent, but it might perform poorly in high dimensions. And so Jason Gorham and Estamaki had a very nice paper, this ICMO, where they were showing this inverse multi-quadratic kernel is actually a better kernel in high dimensions for this testing problem. And so that might be one thing you might want to use. All right, so last of all, I'm going to talk about testing dependence. Okay, so remember my dots and my captions. So here is my dot, here is my caption, and I want to determine whether these dots and captions are dependent, even though it might be rather difficult for me to map from dots to captions. Okay, so here's an obvious approach, right? You would use the maximum mean discrepancy. And you use the maximum mean discrepancy with P being the joint and Q being the product of the modules. And that's a very sensible thing to do. There's a couple of subtleties, one of which is an easy one to get around, and one of which is a little bit difficult. So the easy one to get around is that I don't actually have samples from Q, I just have samples from P, but I can simulate samples from Q, basically by scrambling the ordering of my Y's with respect to my X's. So if I assign a random caption to each animal, then that's a good way of simulating a case where the animals and captions are independent. So that's how I solve that problem. But a trickier problem is actually what kernel to use. Okay, like what's a good kernel that I could use for my maximum mean discrepancy? So I'm going to construct one possible candidate answer for that. So let's say I have a kernel on my images, in this case, here, and I have a kernel on captions. And my goal is to find a kernel between an image caption pair, right? Because I'm computing my MMDs on distributions over image caption pairs. Okay? So the kernel between this image and its caption and this image and its caption, I could define as the product of the kernels. All right? So a crude way to think about this is a sort of and. If the images are similar and the captions are similar, then the overall similarity is large. Okay? So, this seems a little bit arbitrary. And indeed, at this point it is. But let's just run with it and see what happens. Okay. So if I use this product kernel, and if I simulate my product of marginals by using all possible permutations of my labels with respect to my captions, my labels with respect to my images, then this is what the MMD looks like. it looks like the trace of the product of the kernels on the images and the kernels on the captions with some column centering. So why is this logical? So let's go back to our setting, right? Here we've got our images, and here is the kernel between the images. So you see that two dogs have high similarity, but dogs have low similarity to cats. Here is the same. Here is the kernel between our captions. So two dog captions have high similarity, but the dog captions have low similarity with respect to the cats. So you can see that patterns that occur in this view of the object also occur in this view. So if two animals are similar, their captions are similar. If two animals are different, their captions are different. So if I take the dot product of these two matrices and it's large, so these matrices are very similar, then indeed this quantity is large, and I'm concluding that these images and captions are dependent. If this dot product is small, then I'm concluding that the images and captions are independent. So this is a way of measuring the dependence between images and captions without ever explicitly translating from one to the other. And the reason we can do this is we see many examples of image-caption pairs, so we can compare this structure to that structure. So this is a nice intuition. And this arises when I use this product kernel, and I use this means of estimating my product of multiple distributions. So that's fine, and I can do a nice figure of it. But then, first of all, like, why the product kernel? Sums of kernels are also kernels. Why wouldn't that work? And the second is that, like, this isn't ultimately a very interpretable way of illustrating dependence. So if I'm talking to somebody in a laboratory and they give me data and they say, are these data dependent? The method that I just showed you is probably not going to satisfy them very much. They want to say, well, is there some strong linear correlation, say, or something that they're sort of more at home with. All right, so how do I guess, arrive at a statistic which is more compatible with this view? Okay, so here is x and y. I've got samples from x and y, so each of these points is a pair, xy pair. And I compute the linear correlation on this, and it's 0. But clearly x and y are dependent on this, right? So knowing x tells me quite a lot about where y is on this plot. So what's a nice way of taking this and giving an interpretable way of showing that x and y are strongly dependent? So here's one way. I could take my x here, and I could pass it through a smooth function, right? This fx is a smooth function. And I could take my y and I could pass it through a smooth function. And I could choose these smooth functions such that once I've mapped my x through this function and my y through its corresponding function, I get a strong linear correlation. So this is something that, like, if you have a practitioner, they might be a lot happier with this, because they could say, well, I know that these are dependent because if I pass my two variables through smooth, simple functions, they have a strong linear correlation. So that's something that's a lot more interpretable, I think. So how do I get these smooth functions? So because I've got now two functions, I need two feature spaces. I'm going to use the same classes of functions I use for MMD. So basically I've got a function f, which is the sum of smooth features, and a kernel. I've got a function g, which is the sum of, in this case, different features, because it might be that I've got a different class of objects, like images versus captions, and its corresponding kernel. Okay? So now I've got a function class f and a function class g. And these are the functions that I'm going to be using here. All right? So if I use these function classes, right, then I'm going to define something called the constraint covariance, where I'm going to here have f, which is going to be in a unit ball, and g, which is also going to be unit ball, but will maximize my covariance of f and g. So these are the functions that I've just plotted here. These functions are in the unit ball of the classes that I defined on the previous slide, and these functions are the unit ball functions that maximize my linear covariance between f and g. Okay, so that's going to be the constraint covariance. So let's write this out. So remember that my function f of x, I'm going to write as the sum of features of x. My function g of y is the sum of features of y. If my features have 0 mean, I can replace this covariance by an expectation. So it's the expectation of the product of functions. Okay, assuming 0 mean. And then I can take this expectation inside, and now what I've got is like this vector of coefficients f times this expectation of outer products of features of x and features of y times this vector of coefficients g. So what does this look like now? This looks like the maximum singular value of this infinity by infinity matrix of expected covariance between features of x and features of y. Okay? So this is basically the matrix of covariances of every feature of x with every feature of y. It's an infinity by infinity matrix if I have infinitely many features. If I take the largest singular value of this matrix, this is my constraint covariance. And the largest singular vectors correspond to the coefficients of my functions. So that's the constraint covariance. So just like with MMD, it's a little awkward to deal with infinitely long vectors of coefficients and infinitely large matrices. If I have samples from x and y, how do I get the constraint covariance? It turns out, and I won't show the proof, but the proof is actually very short, that you again get a simple problem in terms of the kernels between, on one hand, the x's, so k is the kernel between every x pair, and L, the kernel between every y pair. So this is a generalized eigenvalue problem, where this eigenvalue here is our estimate of the constraint covariance, and then the witness functions are just the sums of the kernels of the x's with weights given by the eigenvectors, up to a constant of proportionality. So, just as before, even though I'm finding functions of infinitely many features, when I compute them on the basis of samples, I can just write these in terms of the dot products of the features, so the kernels between my sample and the point at which I evaluate my function. So this is very convenient. So this is just how to compute these things, but now let's go back to understanding exactly what it is that the constraint covariance is doing. So what, if I'm using this constraint covariance, like what is a large dependence and what is a small dependence? Like how do I say that something is very dependent or something is less dependent? So to illustrate this, I'm going to use a very simple example. Okay, so this example here, I've got a distribution which is basically like an offset, so that it's not negative, plus a product of signs at some frequencies omega. This is a low frequency case, so here I've got my points, scattered according to this density, so I see I've got fewer points here and more points there. And this is the high frequency case, where I've got this very high frequency pattern, and I'm seeing points go from it. All right. So according to constraint covariance, which of these two is more dependent? So let's see. So let's start with this frequency 1. Here are my witness functions, and you can see they sort of push the points up into the corners. Okay. Here the constraint covariance is 0.09. Next case, you see I've doubled the frequency of my oscillation of my witness function. Again, pushes the points in the corners, but the constraint covariance is a little lower, 0.07. And this is because I've got the smoothness constraint, which means that my constraint covariance can't be as big when my functions are required to oscillate more. Now I've got my witness here. I've got even more oscillations. My constraint covariance is dropping, but I'm still managing to push my points into the corners pretty well. Omega equals 4. Here it's a bit iffy, right? My constraint covariance is now 0.02. It's not finding that much dependence anymore. It's omega here. Well, here omega is actually 0. It's completely uniform. There's no dependence between x and y. But my constraint covariance is not quite 0, right? Because even though there is no dependence between x and y, I'm seeing x and y just through their samples. And that means that, because I've got these functions, I can sort of shift the points around a little bit to get some sort of residual covariance. And what this is just bias. I'm saying that I've got some upward bias on my constraint covariance, which is going to drop as I see more samples. Okay? So just to summarize what we've just seen, as the dependence is encoded in higher frequencies, these mappings have lower linear dependence. So this is what I mean when I'm using constraint covariance, when I say that things are very dependent or not so dependent. So very dependent means the dependence is encoded at low frequencies. Not so dependent means it's encoded at high frequencies. Then I also illustrated some bias. All right, so can we do better? Okay, here is our constraint covariance for a simple example where there's no linear correlation. This is what we got when we used the largest singular value of the covariance between the features. What if we use the next highest singular value? We can do that. Okay, so here's the next highest singular value, so it's orthogonal here are the next highest singular functions, which are orthogonal to the first ones. And here you can see that the constrained covariance of these second highest eigenfunctions is a bit smaller. But it's still not 0. So there is still some dependence, which we found, which wasn't found by the top two. Okay? So it actually is useful to look at the next one down. And it's also finding something that is indicative of the dependence. So how might we summarize this? One way to do it would be just to take the sum of the squared singular value, right? Which is basically the Hilbert-Schmidt norm of this infinity by infinity feature covariance. So if we do that, it turns out this is exactly the quantity that we started this section by, which is the maximum mean discrepancy between the joint and product of the marginals using the product kernel. So now we understand what this is doing. This is basically like looking for pairs of functions that have high covariance and summing the sum of the squared covariances that you get over all these pairs of functions. So that's a way to sort of tie in this quite unintuitive thing with the Hilbert-Schmidt independence criteria. So by the way, what is my sort of scheduled end time for this? Because we started a bit late. Does anyone?
Yeah, another 15 minutes is fine.
Cool, yeah, that's perfect. Okay. So this is my statistic. Just as before, we want to do a hypothesis test with this statistic, right? So,
quick question.
Yep.
It's a very basic one. So once you transform the independence test problem into this difference between two distributions, so why can't I ignore, like, why further optimizing for kernels and so on? Like, we could have just used the machinery from the first part of the talk, your presentation, right? And
right, so, I mean, that's how I sort of started that. I said, like, here is my MMD between joint and product of marginals.
Yes.
But, like, if you're using this, like, the kernel that you're using is a little bit arbitrary here. So our original thought was sort of like, sure, you can write that, but what kernel should you use? Should you use a kernel?
But then why did you choose a product kernel? I mean,
so, okay, I will actually, that's a question that I sort of skipped over a little bit. I'm going to answer it a bit better now. So, if you're looking for any difference between P and Q, you need a kernel that sort of has, I would say the terminology, it's characteristic to all distributions. So basically, like, you want a kernel whose features uniquely embed every distribution. So this is something that I didn't talk about in this talk. I just said I have infinitely many features. In practice, it's not enough to have infinitely many features. You also sort of have to verify some additional conditions. So one simple way to do it is to check the Fourier transform of your kernel. If it doesn't vanish on an interval, then it's characteristic. Okay. The issue with using, so that is for maximum discrepancy. Now in this case, right, I might need a characteristic kernel to the distribution jointly over images and captions, and that might be a hard thing to do. But it turns out that when you're testing independence, you're actually asking an easier question. You're not asking, is there any difference whatsoever between pxy and px times py? You're just asking, does this distribution factorize into the product of the marginals? It's a much narrower question. And to answer that question, you can prove that it's sufficient just to use a product kernel where each of the kernels are individually characteristic to their marginals. But you don't need the much harder problem of looking for a kernel characteristic to the joint domain. So that's a very good question. You're right to sort of call me out on having sort of being a bit more rigorous about that. Yeah. Okay. Yeah, so let's go to a statistical test. So if you recall the empirical expression of this, I should have said actually also the reason for this name, the Hilbert-Schmidt independence criterion, is because I'm computing the Hilbert-Schmidt norm of this infinity by infinity covariance. Okay, so that's the reason for this name. Yeah, so here is the empirical expression of this quantity. And I want now to make a statistical test. So I want a threshold which my statistic will exceed with low probability when P and Q, when Pxy factorizes into the product of the marginals Px times Py. All right? Unfortunately, just as before, we've got something of a problem, which is that under the null, this quantity here is again an infinite weighted sum of chi-squareds. And I put this expression down here, not for people to read it, but just for people to be frightened by it. It's very nasty. So these coefficients are again difficult to estimate from data. Okay, so again we need some threshold such that the probability of exceeding this threshold is less than alpha for some small alpha probability when pxy factorizes into the product of the marginals. Okay, so what's the way that we're going to use to simulate from this now? So remember, for the NMD we had this permutation idea where we throw everything in a bag and then assign half to p after q. For independence testing, there's another form of permutation that we can do to simulate from the product of the marginals. Okay, so here's our original time series. We observe x1, y1, x2, y2, x3, y3. Okay, the permutation here is that we shuffle the y with respect to the x. So we assign a random y to each x. x1 gets y7, x2 gets y3. Okay, so if I compute the h-sig with this shuffle data, that's simulating from the h-sig that I would have if it were true that x and y were independent. Okay, so I repeat this shuffle many, many times. I get a histogram with the kind of typical h-sigs that I would get if x and y were independent, and I use the quantile of that shuffled distribution for my num. And that works when it's consistent. Again, though, you can use the gamma if you want to sort of do some computationally cheaper things. The gamma works most of the time, but it isn't consistent, so you can find distributions that break it. All right, so let's now move to a practical illustration. Here we have x and y. The x variables are little fragments of text from Canadian Parliament transcripts in English, and the y are the corresponding fragments in French. Okay, so our x-y pairs are like, this fragment here, honorable senators, I have a person, blah, 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 and then this is the French one, honorable senator, etc. Right? I have all of these pairs, and I want to determine whether the x and y are dependent or not, assuming that I don't speak English or French. Okay? So how do I do this? So remember our initial illustration with the animals and their descriptions. I assemble here a matrix of kernels between every pair of English fragments. Okay, so each of the little pixels in this image represents the similarity of one of these fragments of text in a second one. Okay? The kernel that I'm using is a k-spectrum kernel, which is basically counting the number of matching substrings, allowing for things like wildcards and incomplete matches. Okay, so it's actually quite a good kernel for text. I now do the same for the French text. Okay, so I find the similarity between every fragment of French text and every other fragment using, again, a substring kernel, and I get this matrix here. So I've never translated from English to French. Okay, I've just found the similarities between every French text and every other French text in this matrix, and the similarity between every English text and every other English text in this matrix. Okay? And now what's my h-sig? It's just the dot product of this matrix and that matrix, right? So if for every similar English text pair there is a similar French text pair, and for every pair of English texts that are very different, the corresponding French texts are very different. And if this pattern occurs over and over and over again, then this dot product is going to be large. These matrices, if you squint at them, they look pretty similar. But if I scramble the contents of this matrix with respect to this one, then this dot product will be small, because I've now randomly assigned French text to my English text. So this is a nice intuition. How well does it work? Well, it works extremely well, so the probability of mistakenly thinking that the translations are not correct is 0. But this is actually a function of the powerful kernel that we use. So if you use a CUDA kernel, which is just a bag of words kernel, then we get a much higher rate of false negatives. All right. I think, let's see, I can just give a quick 5-minute taste of higher order interactions. Okay. Because this is UAI, I think graphical models are very interesting. I might want to test whether, this kind of structure occurs in my data. So now I've got 3 variables rather than 2. Okay, so I've got independent parents, but I've got parents that are x and y dependent conditioned on z. Okay, and the case that I'm specifically interested in is the case where these links are weak on their own, but the joint effect is strong. So if I've got a chemical reaction here and I just apply heat and no catalyst, then will speed up a little. If I apply catalyst and no heat, it will speed up a little. If I apply heat and catalyst together, I get an explosion. So that's the kind of task that I'm interested in. Okay? So here is an illustration of this in simplified data, where here x and z individually could be independent, y and z could be independent. So this is, of course, violating faithfulness, but we can sort of weaken this a bit to make it plausible. But then taken together, x and y have a very strong dependence on z. Okay? So some approaches we could use are conditional independence tests or factorization tests. The trouble is that testing conditional independence is hard. So if I take this example here and I add some noise dimensions, I'm going to show you what happens. Okay, so on this axis I'm adding more and more noise dimensions to my V structure. And here is the rate of accepting the null hypothesis, so not noticing that there's this V structure. And you can see that these sort of earlier approaches rapidly fail as dimension gets high, because testing conditional dependence in high dimensions is hard.
So what is noise dimension?
So basically, like I've got my x and y and z here, which are univariate, and then I just add random Gaussian noise for all the remaining dimensions. So it just jumps, basically independent jumps.
Additional nodes or additional nodes?
Just pure noise, uncorrelated Gaussian noise to dimensions. Like a dimension 1 is what's in these terms.
By dimension you just mean node of the graphical model.
Sorry?
Node of the graphical model.
Yeah. So to each of the 3 nodes, I'm just adding, I'm appending additional noise vectors to my x, to my y, to my z, just to put it into high dimensions and to add junk that isn't informative about the V structure that I'm looking for. Yeah. And this is, it becomes hard, basically, when I'm adding this noise. So what I can do, this is the quantity that I was dealing with independence. For 3 variables, I can define this quantity here. So this is quite a complicated looking one. I've got pxyz minus pxyz minus pypxz, etc., etc. So what does this look like graphically? This is my joint distribution. The first term I break x off yz, the second term I break y off xz, the third term I break off z, and then this is just the jointly independent variables. So this is sort of illustrating what this is. Okay? So this is a signed measure which is going to be 0 in the case where I have any kind of factorization of my 3-variable distribution. Okay? So let's say that it's true that x is independent of yz. Okay? So then, this is actually true, so these two cancel. And then these are all the product of the px, py, pz. So these all cancel, and then I'm, this signed measure is 0. So basically, if any of these factorizations occur, z breaks off xy, y breaks off xz, etc., then this is 0. Okay? What might be missed, unfortunately, if this is 0, it doesn't imply that. Okay? So that's unfortunate. So I can create a distribution which is completely dependent, and yet this is 0 for. Okay? So what this means ultimately is that if I reject the null, so if I find that this is large, then I can conclude that the distribution doesn't factorize. If this is 0, all bets are off. I don't know what I can do, so I have to use a proper conditional independence test. But let's get through this stuff. When I use the kernel embedding of this signed measure in a test, it's much more powerful in high dimensions. So when it works really well because it's doing something a little simpler than a conditional independence test. And so it's working even in this case where individually the links are weak, but jointly they're strong. Okay, so I think this is a good stop. So I will take questions now. So thank you. Okay.